Welcome to the Deep Dive, where we plunge into complex source material and emerge with the essential, fascinating insights you need to be truly well-informed. Today, we are wrestling with a question that I think really defines our place in the cosmos. Can humanity, using the known laws of physics, actually communicate across the immense gulfs of light years that separate star systems? Our source material for this analysis is pivotal. It's Joseph Shklovsky's towering work, Universe, Life, Mind. And we're focusing specifically on the chapters where he and his contemporaries, names like Cocconi and Morrison, laid the absolute technical foundation for interstellar radio communication. They really shifted the question from a philosophical debate into a concrete engineering challenge. So our mission today is not to speculate if extraterrestrial life exists. Instead, we're going to unpack the rigorous scientific and mathematical proofs that established decades ago that radio contact is technologically achievable, provided an advanced civilization is actually out there transmitting. And this is the core thesis we really have to get our heads around. The search for extraterrestrial intelligence, or SETI, depends on solving hard physics problems, not just hopeful belief.
And that framework, distinguishing between the physics and the metaphysics, that's really where the analysis has to begin. When Shklovsky was writing this, the statistics were already overwhelmingly suggestive. The sources make it very clear. Our galaxy contains at least several 100 million planetary systems.
Several 100 million? That's a staggering number.
It is. And if we assume that life, driven by just basic chemical reactions, arises whenever conditions are stable, which is a pretty reasonable assumption, then we are potentially looking at a similar number of inhabited worlds. The sheer scale of the cosmos just dictates abundance.
But the jump from inhabited world to technological civilization is,
Yeah.
well, it's a canyon we have to cross, isn't it? The numbers might suggest life is common, but the big philosophical hurdle is whether that life is likely to become intelligent.
Precisely. And this is the crucial uncertainty that defined all of the initial debates. Shklovsky is very, very clear on this. Intelligence is not a guaranteed result of biological evolution. This source explicitly refutes that earlier, almost idealistic view, which was prevalent among some philosophers, that the ultimate purpose of cosmic evolution is the inevitable emergence of thinking beings.
It's a pretty sobering argument when you think about it.
It's rooted in our own terrestrial history. We often forget that the vast majority of Earth's existence, billions and billions of years, occurred without any form of technologically intelligent life.
Right. We're a tiny blip at the very end of the timeline.
A negligible duration. Homo sapiens, even if you take the broadest definition of the genus Homo, has only been here for maybe 1 million years. Evolution doesn't necessarily favor tool-using intelligence. It just favors survival.
And if intelligence isn't an inevitability on every inhabited world, then the entire structure of the search, the whole premise, it collapses down to a single unknowable variable.
It boils down to the probability that life, once it gets started, evolves into intelligence and then develops technology. We can, denote this as life intelligence.
And that probability is what exactly?
It's totally unknown. And it remains the central mystery of SETI even today. You essentially have two extreme camps.
The optimists and the pessimists.
Right. The optimistic view holds that the probability is near unity, so close to 1. The idea is that given enough time and enough biological variety, technological intelligence is almost guaranteed to emerge. And if that's true,
then the galaxy should be teeming with civilizations.
Absolutely. The great silence becomes a real paradox.
And the opposing pessimistic view.
The pessimistic perspective suggests this probability is vanishingly small, maybe 10 to the minus 6 or even 10 to the minus 9.
So 1 in a million or 1 in a billion?
Exactly. This implies that the specific confluence of events that led to human intelligence, the right extinction events, the specific environmental pressures, the timing of it all, is incredibly rare. It could potentially make Earth unique, at least within the confines of our own galaxy.
And that uncertainty was a major point of contention at the time.
Oh, a huge point. This profound existential uncertainty was the subject of intense debate at major scientific gatherings, most notably the Burakin Symposium. The sources underscore that while the abundance of worlds is statistically proven, the abundance of intelligent worlds remains purely speculative.
Which forces the search to focus on technological capability rather than just philosophical optimism.
It has to. You can't build a radio telescope based on hope.
Right. And the stakes are just immense because of that statistical uncertainty. Even if the probability of contact is low, the overwhelming importance of a successful search, that drives the commitment. Establishing a link with a civilization that is, say, a few 100,000 years ahead of us technologically, which they almost certainly would be, just given the age of the galaxy, would deliver an incalculable impulse to human society.
This is what Cocconi and Morrison called the communication imperative.
And when they first rigorously analyzed the technical possibility of this kind of exchange back in 1959, they immediately narrowed the field. Okay, let's unpack this. Why did they immediately settle on electromagnetic waves? They had to find a vehicle that satisfied three primary physical constraints for interstellar travel.
Maximum speed, efficient energy concentration, and minimal scattering.
Right. And electromagnetic waves radio offer the speed of light, which is obviously non-negotiable.
It's the cosmic speed limit.
And they can be focused into narrow beams, which minimizes power loss over vast distances. No other known physical medium offers that trifecta.
So having chosen radio waves as the communication medium, the next Herculean task was identifying the optimal road, the specific frequency or wavelength that provides a clear channel through the cosmos. Interstellar space is vast, but it's not truly empty. It's filled with gas, dust, and magnetic fields. And our signals also have to penetrate planetary atmospheres. We need a frequency range that minimizes absorption across all of these different environments.
So you have to find a window that works for both the journey and the arrival.
Precisely. And this led to the definition of the frequency boundaries, the fences that constrain our workable window. The first is what they call the low frequency barrier, which involves very long wavelengths.
And that's the barrier related to the interstellar medium itself, right? The stuff between the stars.
Yes. Very long waves, low frequencies, are heavily absorbed and scattered by the partially ionized plasma that permeates the vast spaces between stars. The sources estimate that the maximum acceptable wavelength before this interstellar absorption becomes crippling is around 300 meters.
Which corresponds to what, about 1 megahertz?
About 1 megahertz, yes. But that's just the space constraint. For an Earthbound civilization trying to communicate with another Earthbound civilization, the crucial atmospheric constraint is the ionosphere.
Our own atmosphere gets in the way.
It does. Our planetary upper atmosphere contains this layer of partially ionized gas, and this layer acts like a reflector for very long waves. To penetrate the ionosphere and actually reach a ground receiver, the wavelength has to be significantly shorter, generally shorter than 10 to 15 meters.
So even if the interstellar medium allowed 300-meter waves to pass, Earth's ionosphere screens them out anyway. We are restricted to shorter waves by our own planet's atmosphere.
Exactly. Then we hit the other side of the spectrum, a high-frequency barrier or the short wavelength limit.
And this is related to molecules, specifically things like water vapor.
That's correct, and it really highlights why local planetary chemistry matters so much. As the wavelength gets shorter and shorter, we enter the microwave and millimeter bands. On a planet like Earth, common atmospheric molecules, primarily water vapor and oxygen, begin to absorb this radiation, almost like a filter.
And that absorption kicks in at a specific point.
It does. For water vapor, significant molecular absorption starts right around the 3-centimeter wavelength. So that forms the upper frequency limit for ground-based radio astronomy.
So you've got these two hurdles, the 10 to 15-meter minimum imposed by the ionosphere and the 3-centimeter maximum imposed by atmospheric molecular absorption.
And when you combine them, you define the initial terrestrial window. This is the primary workable range for any early SETI search that's using powerful, fixed radio telescopes on the ground.
It's important to pause and note the contingency here, though. The source mentions that if humanity or any advanced civilization were to place its receiving and transmitting equipment outside planetary atmospheres, so on dedicated orbital platforms or moon bases, these atmospheric absorption limits would just vanish entirely.
That's a critical piece of expert insight. Orbiting receivers, for example, could operate perfectly well in the millimeter and sub-millimeter bands. It would significantly expand the workable frequency range.
And it would eliminate the thermal noise generated by the atmosphere itself, right?
Completely. But for the initial feasibility defining searches, you have to deal with the limitations of being earthbound.
Okay, so once we've restricted the channel based on absorption, we move from structural limitations to energy limitations. The sheer distance means signals are attenuated to almost nothing. This makes background noise, the universal static, our primary adversary. So we have to understand the noise temperature spectrum to find the quietest possible segment of the cosmos to listen in.
And that noise comes from 3 distinct sources, each one dominating different parts of the spectrum. First, you have cosmic noise.
The galaxy itself humming.
That's a good way to put it. It's the continuous, broad radio emission from the entire galactic plane and the metagalaxy. It is the static generated by natural processes. synchrotron radiation, thermal emission from gas clouds, and its intensity increases dramatically as the frequency decreases. That's why the low-frequency end of our window is so incredibly noisy.
So we have the absorption barrier at low frequencies,
Mhm.
and then immediately above that, the cosmic noise interference just dominates. What about the high-frequency side?
That's dominated first by what we call thermal noise. This is simply the heat radiation from matter, specifically from planetary atmospheres. As you move into the centimeter, millimeter, and submillimeter bands, the atmosphere itself starts radiating thermal energy. It's like it's acting as a noisy blanket.
And that's unavoidable for ground-based receivers.
Completely unavoidable. And then finally, you have the most fundamental limit of all, quantum noise.
The noise of physics itself.
Yes. Even if you built a theoretically perfect receiver operating in a vacuum at absolute zero, you would still have noise. This is the intrinsic, unavoidable noise generated within the receiver components, and it's a consequence of the discrete, quantized nature of radiation flow.
This is the famous one-octillar term we see in the formulas. Can you clarify what that constant means physically?
Certainly. So Hano represents the minimum energy quantum, or the photon energy, which is proportional to the frequency delivered via Planck's constant dollars. And a Hahner is Boltzmann's constant, which links temperature to energy. At high frequencies, the individual energy quanta, the photons, become more and more energetic. The quantum noise limit means that as you try to listen at higher and higher frequencies, the discrete nature of energy makes the measurement inherently jumpy and uncertain.
So it increases the baseline noise temperature.
It does. This is why quantum noise dominates the very highest end of the spectrum.
So we have low-frequency noise from the galaxy, mid to high-frequency noise from our own atmosphere's heat, and then ultra-high-frequency noise from the fundamental limits of physics itself.
It sounds like a complex noise bowl.
It is. But when you overlay all three of these sources, the cosmic noise, the thermal atmospheric noise, and the quantum apparatus noise, they create a very distinct U-shaped curve on the noise temperature spectrum. The sources often depict this as figure 41, and the bottom of that U-shaped curve represents the region of minimum background noise. Here's where it gets really interesting, because the analysis showed that the quietest place in the entire radio sky, the critical quiet window that any technological civilization would inevitably gravitate toward, occurs between 5 and 10,000 megahertz.
Yes. That's the wavelength band spanning 30 centimeters down to 3 centimeters. Not only is it clear of major atmospheric absorption, except at the very short end, but the combination of all that background static is at its lowest possible point.
So any rational technological civilization designing an omnidirectional beacon would place it right there in that window.
They would have to. It offers the highest possible ratio of signal to noise. It's just smart engineering.
We've identified the quiet channel, 1,000 to 1,000 megahertz. But now we have to address a significant local obstacle. If a civilization is transmitting from a planet orbiting a star, that star is an incredibly powerful radio source. It's right next to their antenna. How can a faint artificial signal avoid being completely drowned out by its own sun?
That's the logical next hurdle, and it's a very important one. A star like our sun is a colossal, continuous radio emitter across all frequencies. To ensure detectability, the artificial signal's power, within its extremely narrow frequency band, must be comparable to the star's natural emission in that same band.
So let's ground this with the sun example. What kind of power are we talking about?
Using a specific frequency, say the 10-centimeter wave, the quiet sun, and that means the sun, when it's not experiencing flares or intense storms, radiates like a heated black body at an equivalent temperature of about 50,000 Kelvin. Using the Rayleigh-Jeans approximation for low-frequency radiation, we can calculate the spectral density of this emission. The power output is approximately 2.6 times 10 to the 3 watts per hertz of bandwidth.
2.6 kilowatts of natural stellar power in every single hertz of bandwidth. And a planetary civilization has to compete with that. It sounds impossible for a focused beam.
It would be if the star and the transmitter were broadcasting in the same manner, but they are not. The key differential is directionality. The star radiates isotropically equally in all directions. It's like a bare light bulb. The civilization's transmitter, however, is not a star. It's an intelligent machine using a highly focused parabolic dish. It's like a laser pointer.
So the artificial signal can be focused into an extremely tight, narrow cone.
Precisely. The angular width of this beam, theta, is approximated by the ratio of the wavelength to the antenna diameter, and the concentration of power achieved by focusing is called gain, represented by dollars.
Let's quantify that gain, because that's the real equalizer here.
Okay, let's take a plausible large radio telescope, maybe 300 meters in diameter, operating at a 10-centimeter wavelength. That massive antenna, by focusing the signal, provides a gain of approximately 10 to the 8.
100 million.
100 million times greater power density concentrated in the direction of the beam compared to if that energy were just radiated diffusely.
100 million times. That radically changes the required power.
It flips the narrative entirely. The sources show that when you factor in this gain, if the transmitter power utilized by the alien civilization is only about 10 to the minus 5 watts per hertz, a microscopic fraction of a watt, the focus signal directed towards us will already be comparable in intensity to the sun's background radio noise.
That's incredible.
The conclusion is just undeniable. Stellar radio emission is not a practical hindrance to interstellar radio communication. We can easily overwhelm the star's noise through the application of focused beam technology.
So the physics is solved. We have the quietest channel, 1,000 to 10,000 megahertz, and we know how to bypass the star's local noise. But that quiet window is still 9,000 megahertz wide. If an alien civilization is trying to signal us with a narrowband beacon, how do we know exactly which frequency to tune into? We need a universally recognizable landmark. This brings us to probably the most elegant and famous solution ever proposed in this field. From Cocconi and Morrison, the universal language of the hydrogen line.
The universe provides a definitive standard frequency that transcends language, biology, and planet of origin. The 21-centimeter radio line of neutral hydrogen. This corresponds to 1,420 megahertz, and it sits perfectly within that quiet window we just defined.
And the logic behind it is just so compelling.
It's compelling because it's based on objective reality, not on culture. Hydrogen is the most abundant element in the entire cosmos. Any civilization at a relatively modest level of astronomical sophistication will discover and map the universe using this 21-centimeter line. It's the background hum of the galaxy.
So 1,420 megahertz isn't just a frequency, it's a universally understood fundamental reference point.
The laws of nature are the same for all intelligent beings. It's the ultimate Schelling point.
That rationale grounds the search in materialism, not assumption. But if 1,420 megahertz is the obvious standard, are there arguments for alternatives? Maybe they assume we are smarter and are looking somewhere else.
Absolutely. The one problem with 1,420 megahertz is its own popularity, so to speak. Because neutral hydrogen is everywhere, the sky noise can be relatively high at 21 centimeters up to 50 or 100 Kelvin, particularly when we look directly into the dense galactic plane.
So the line itself can be noisy.
It can be. So some scientists propose that an advanced civilization might choose a harmonic frequency, or a multiple, to broadcast on a cleaner channel.
For instance.
For example, they might use 2,840 megahertz. That's double the hydrogen frequency. At this doubled frequency, the sky noise from diffuse sources drops significantly, often below 10 Kelvin. This might be a deliberate, higher-tech choice for ultra-clear transmission.
And then there's the even more ambitious proposal from the Soviet scientist Nikolai Kardashev, looking far outside the hydrogen band entirely.
Yes, Kardashev suggested moving all the way down to the 1.5 millimeter wavelength. Now, this band has the unique property that the sky brightness temperature is at its absolute lowest, dominated only by the faint 2.7 cosmological background radiation, the residual heat from the Big Bang.
The ultimate quiet spot.
The ultimate quiet spot. For civilizations aiming for communication across truly vast metagalactic distances where even 10 Kelvin of noise is too high, the 1.5 millimeter band might be the most economic choice. And interestingly, this wavelength also happens to coincide with the radio line of positronium, an exotic electron-positron atom, providing another potential natural reference point, albeit a much more obscure one.
So whether they choose the hydrogen line, its harmonic, or the deeper cosmological window, the channels exist. Now, we have to move from defining the channel to proving the power requirements. We have to definitively show that the math holds up.
And this is where Shklovsky's work really drives the point home, by quantifying the relationship between signal and noise. In radio astronomy, the received signal strength is measured by what's called the antenna temperature, TTA1. And the simple rule for detection is that the signal temperature must be greater than the background noise temperature, so TTA-A1.
And the formula for that antenna temperature is, it's a bit complex.
It is, but it's fundamentally proportional to the product of the transmitter power, the size of the transmitting and receiving antennas, d-dollars and d-dollars squared, and then it's divided by the square of the distance and the square of the wavelength.
That $2 in the denominator is the painful part.
That's the inverse square law. It's the tyrant of interstellar communication.
Let's trace Shklovsky's original argument, what you call the 10 light-year proof. This was revolutionary because it used technology that was available at the time of writing.
It was a sanity check, really. Let's assume modest, achievable parameters. Both the transmitting and receiving antennas are 100 meters in diameter. We assume a transmitter power of only 100 watts per hertz using a 10-centimeter wavelength. If we set the signal temperature equal to the background noise temperature, the absolute minimum required for detection, and then solve for the distance, $2, the calculation yields approx 1019 centimeters.
Which translates to about 10 light years.
Exactly. And the implications were stunning. It proved, mathematically, that the level of radio technology already available on Earth in the 1950s, before masers and huge modern arrays, was already sufficient to achieve radio contact with the closest star systems.
It wasn't about building science fiction devices.
Not at all. It was about pointing existing equipment in the right direction. And that realization provided the scientific impetus for projects like Project Ozma.
But 10 light years is incredibly restrictive. We know, based on the negative results from those earliest searches, that any civilization is likely much farther away. So how do we expand that detection range without increasing the transmitter power to impossible levels?
This is where we have to move beyond that simple TTL to DD criterion and factor in the advanced technology that came later, specifically the concepts of accumulation time and the reduction of apparatus noise.
Okay, let's start with the unavoidable limit. Receiver fluctuations. Even with a perfect constant input, the measured output of the receiver is going to fluctuate.
That's right. The signal measurement is fundamentally limited by unavoidable statistical fluctuations, which we call delta T, within the receiving apparatus. The formula that governs this limitation, the fluctuation limit, is delta TT is with 1 scarta 5.
And in that formula, T-taus is the overall noise temperature, delta Z is the frequency bandwidth.
And tau is the crucial variable, the accumulation time.
So we can improve our signal by making our bandwidth narrower, or by making our accumulation time how long we stare at the source longer.
Absolutely. The principle of accumulation time is fundamental to detecting weak signals. Imagine trying to hear a whisper across a noisy room. If you listen for only a split second, you hear nothing but static.
Right.
But if you listen intently for 10 seconds, the random, incoherent noise starts to average out, allowing the coherent, repeated whisper, the signal, to emerge above that average background. By increasing tau, we allow the receiver to integrate the signal energy, effectively reducing the impact of random noise fluctuation.
And the other big leap was in the receiver technology itself.
The second massive leap in capability came with innovations like the maser amplifier. These devices dramatically lowered the apparatus noise temperature within the receiver itself. A maser microwave amplification by stimulated emission of radiation works at a quantum level, operating near absolute zero. By chilling the amplifier, you suppress the thermal agitation, the heat, that causes so much of the apparatus noise.
So by lowering U$ and increasing tau, we can drastically reduce that fluctuation limit, delta tau, which means we can detect a signal whose antenna temperature, TDAD, is actually much less than the total background noise temperature.
Exactly. We only need TDAG to be greater than or equal to delta TAJ.
And this shift in technology allows us to perform the second, much more ambitious calculation, the 30 light-year proof.
Let's apply these more modern parameters. We assume we're using advanced equipment, like a maser, achieving an apparatus noise temperature of only 50 Kelvin, a massive improvement over earlier receivers. We assume modest antennas, still 100 meters. But crucially, we increase the time we look. Y equals 100 seconds, so about 1 minute and 40 seconds of integration time. And we use a narrow bandwidth, delta F equals 100 and 404 hertz.
And with those numbers, what's the result?
Using the complete fluctuation formula, we can calculate the required transmitter power needed to maintain communication at 10 parsecs, which is roughly 30 light-years away. The result is what convinced the scientific community of large-scale feasibility. The required transmitter power is only 10 kilowatts per hertz.
10 kilowatts per hertz to reach 30 light years. That's astonishingly low.
It is scientifically trivial. For cosmic context, just recall that the sun's total isotropic radio emission in the decimeter band is on the order of 10 to the 9 kilowatts a billion kilowatts. We are talking about achieving interstellar contact using a highly focused narrowband beam requiring the power output of a small municipal substation.
So the lack of contact is clearly not due to fundamental physical limits.
No, it's due to the sheer probability of finding the right needle in the immense haystack of the galaxy.
Okay, so the contact is possible, and the required power is modest. Now, if we do pick up a signal, the single most important task is confirming its artificial origin. It has to have an undeniable fingerprint that proves it's not just a pulsar or some strange natural cosmic phenomenon.
It has to be immediately recognizable.
First, the signal power must be actively varied. It has to be modulated in a non-random pattern. Second, the signal needs intellectual structure. Shklovsky suggested it might consist of a regular sequence of short pulses, perhaps depicting the natural number series. 1 pulse, pause, 2 pulses, pause, 3 pulses, and so on.
And the idea there is that the concept of discrete mathematics, the sequence of natural numbers, is universal to any intelligent, calculating civilization.
It's the simplest message with the deepest meaning.
Exactly. But the structure must also respect the physics. Because we rely on that accumulation time, individual pulses can't be too short. If a pulse is shorter than our accumulation time, we lose the detection advantage.
So the first message won't be a quick hello.
Probably not. The initial hello messages are likely to be simple, highly repetitive, and potentially long, lasting several hours or even days. This ensures maximum detectability and allows us time to confirm the artificiality before any complex information exchange begins.
But the absolute, undeniable proof that the signal is coming from a technological civilization orbiting a planet lies in the dynamics of the signal itself. The universal fingerprint of motion, the Doppler effect.
This is perhaps the most elegant piece of physics in the entire search. We look for a predictable, periodic change in frequency caused by the transmitter's motion relative to our receiver. And because the transmitter is operating on a planet, it has 2 distinct measurable motions, orbital and rotational.
Let's start with the orbital motion, the planet's year.
The orbital speed of an exoplanet is typically tens of kilometers per second. This speed causes a large periodic frequency shift. And because the speed is so high, the resulting frequency changes can be substantial, potentially hundreds of kilohertz. Importantly, these large shifts often exceed the narrow bandwidth of the signal itself.
So you'd see the signal drifting across your detectors.
You would. And if we plot this frequency change over time, we see a wave, a sine wave. The period of that wave instantly reveals the duration of the distant planet's year. And that is unmistakable evidence of a body in orbit around a star.
That's phenomenal. But the planet's also spinning on its axis. We should see another subtler shift related to its day.
Exactly. The planet's daily rotation causes periodic frequency changes due to the movement of the transmitting antenna across the planet's surface. Since the rotational speed is typically lower than the orbital speed, these frequency changes are smaller, potentially staying within the narrow bandwidth of the signal.
A wobble on top of the bigger wave.
That's a great way to think of it. And through tireless, careful observation, looking for these smaller, faster periodic changes, we can reveal the length of the planet's day. These 2 distinct periodic wobbles, the long period of the year and the short period of the day, are the ultimate proof that the signal originates from an intelligent technological source fixed to a rotating, orbiting body.
So is it truly possible to determine detailed physical characteristics about a planet 30 light years away just from how its radio frequency wobbles?
Absolutely. The laws of celestial mechanics are objective and universal. Once we identify the star class from our own observations, we can estimate its mass. Then, using the orbital period derived from the Doppler shift, the length of their year, we can apply Kepler's third law to calculate the orbital distance of the planet from its star.
And from there you can estimate temperature.
Right. Knowing the star's energy output and the planet's orbital distance allows astronomers to calculate a rough estimate of the planet's average surface temperature. This gives us our first real clues about its potential habitability, all derived without decoding a single word of the message.
And the detail continues to layer on. You mentioned you can combine the length of the day with the amplitude of the daily frequency changes.
Yes, since the maximum amplitude of that daily frequency change is determined by the speed of the planet's surface at its equator, and we know the length of the day, we can actually determine the planet's physical radius.
So you can figure out how big the planet is.
You can. And if the signal is received clearly enough, further sophisticated analysis might even determine the approximate latitude of the transmitter location itself, based on how the daily rotational shift is observed relative to the planet's axis. The physics provides us with a comprehensive astronomical profile of the source, simply through the universal phenomenon of motion.
Given this rigorous proof of feasibility, the idea moved rapidly out of theory. It didn't take long for scientists to move from paper to parabolic dish.
Not long at all.
In 1960, Frank Drake launched Project Ozma at the National Radio Astronomy Observatory in Green Bank, West Virginia. This was the inaugural attempt at modern SETI, and it was specifically targeting that 21-centimeter hydrogen line.
The technical implementation of Osmo was highly sophisticated for its time. The core setup was a highly stable, narrow-band superheterodyne receiver, tuned precisely to 1420 megahertz. The system's biggest challenge was picking out a narrow, coherent artificial signal from the broad, incoherent hiss of natural background noise.
So we need to understand how Drake achieved that near-maximal sensitivity. How did the equipment isolate that faint whisper?
The secret lay in the ingenious modulation scheme implemented on the 27-meter antenna. The antenna used two separate feed horns, and it would rapidly and alternately point at the target star and then an adjacent blank patch of sky cycling between the two positions at a rapid rate of 5 hertz.
So it was switching back and forth 5 times a second.
Exactly. The useful signal, if it existed, would only be present when the antenna was pointed at the star. By switching back and forth, the artificial signal was converted into a pulsed alternating current, while the vast continuous background noise, which was present when pointing at both the star and the empty sky, remained constant.
So the detector was just looking for the signal that varied at precisely 5 times per second.
Precisely. A synchronous detector was employed, an electronic circuit designed to lock onto and isolate the component of the incoming current that matched that specific 5 hertz switching frequency. This mechanism allowed them to achieve a sensitivity very close to the theoretical limit defined by the fluctuation formula we discussed earlier.
Making detection possible even when the signal was weaker than the background noise temperature.
Correct.
Drake targeted 2 nearby G-class stars, Epsilon Eridani and Tel Ceti, both about 11 light-years away. The observation spanned several months, despite the ingenuity of the setup.
The result was negative. No signal detected.
And that negative result, while disappointing, was a really necessary calibration for the search, wasn't it?
It was. It forced the scientific community to accept the likelihood that the nearest technologically advanced civilizations are probably much farther away than just 11 light years.
And subsequent observations in the 1970s, using much larger 100-meter and 45-meter telescopes, continued the search, but also yielded negative results.
Yes, and these deep, sensitive searches confirmed that no narrowband transmitters exceeding several megawatts were operating near any of the stars that were investigated.
This immediately highlighted the crucial challenge, the sheer distance and the scope of the search. If the nearest civilizations are, say, 100 light-years away, we're looking at tens of thousands of potential target stars.
And systematically searching all of them, one star at a time, using the methods of Ozma, just became too complex and expensive. The problem wasn't physics anymore, it was one of overwhelming astronomical resource allocation.
And the necessity of overcoming this distance barrier spurred proposals for massive, almost generational technological leaps in infrastructure.
Frank Drake himself reported at the Bayerican Symposium on the incredible potential of the giant 300-meter Arecibo radio telescope in Puerto Rico. Arecibo's vast collecting area made its theoretical capacity just astonishing.
What kind of range are we talking about?
If Arecibo were paired with a powerful transmitter, say 1,000 kilowatts, and it utilized that long accumulation time of 100 seconds, signals could theoretically be detected from objects up to 6,000 light-years away.
6,000 light-years?
Yes. This pushed the search far outside our immediate stellar neighborhood and into the larger structure of the galaxy if, and it's a big if, we could accurately target the general class of objects to listen to.
Meanwhile, various international efforts are taking place at the same time.
Indeed. The Soviet efforts, led by V.S. Troitsky, systematically searched about a dozen G-class stars in the 30-centimeter range, ranging from 10 to 60 light-years distant.
And they found the same null results.
The same null findings. But the most ambitious proposal born from this era was probably Project Cyclops, championed by Bernard Oliver in the U.S. The initial searches were limited by existing equipment, but Cyclops proposed a dedicated, vast radio telescope array.
Not a single dish.
No, not a single dish, but a massive collection of up to 1,500 individual 100-meter antennas spread out over miles. The idea was that this array, linked electronically, would function as one single colossal dish, maximizing both collecting area and resolution.
That sounds like a multi-billion-dollar project. What was the driving rationale for that kind of investment?
The rationale was simple. You need that level of sensitivity to defeat the distance challenge. Cyclops was conceived as a multi-decade generational project that would allow systematic searches of the entire galaxy for narrowband signals. Its estimated cost really reflected the scale of the commitment required to move the search from a sporadic, small-scale scientific experiment to a comprehensive, continuous monitoring effort.
And there were other similar ideas floating around.
There was a parallel, slightly less expensive idea called the Global Radio Telescope concept, proposed by UN Perisky. Instead of building a new, dedicated array, this proposal focused on linking all the major existing radio telescopes on Earth, Arecibo, Green Bank, the Russian dishes electronically, potentially even including space-based units.
Creating a virtual dish the size of the Earth.
Essentially, yes, achieving resolution and sensitivity far beyond any single instrument.
These proposals, while visionary, they highlighted the reality that the search had entered an expensive waiting game. And that's why the research that turned the focus back onto Earth is so instructive. Sullivan and Knowles used the Arecibo antenna to study Earth's own radio spectrum by observing signals reflected off the Moon. They asked, if they exist, how visible are we?
They were measuring Earth's radio footprint, and the results showed that Earth is not quiet, not at all. Our spectrum is dominated by terrestrial sources, primarily television broadcast stations, heavily concentrated in the 150 to 500 MHz band, which is actually below the 21-centimeter hydrogen line.
What's the most powerful signal we're currently leaking into space?
The single most powerful signal observed was from a U.S. radar system operating at 217 MHz, emitting pulsed energy at a staggering 14 billion watts.
14 billion watts.
Pulsed, yes. And if a civilization with an gazebo-sized antenna were listening, they could detect these specific radar pulses from up to 20 light-years away. Even our strong, continuous television signals, though much, much less powerful, could be detected up to about 3 light-years away.
So what does this tell us? We are visible, but really only to our most immediate neighbors in the stellar community.
Precisely. Our current radio leakage provides a modest, detectable sphere of maybe 20 light-years. However, the searches we are conducting are designed to detect signals that are hundreds, if not thousands, of times stronger than our own diffuse leakage signals from highly focused, narrowband transmitters that are far more efficient than our terrestrial broadcast networks.
So what does this all mean? Let's summarize the technical landscape of the search, based on the physics Shklovsky and others pioneered.
The core takeaway is technological feasibility. The physics is not the limitation. We proved decades ago that the basic properties of radio waves, combined with modern receivers like masers and enormous antennas, make interstellar communication possible. We only need a modest 10 kilowatts per hertz of focus power to bridge distances up to 30 light-years.
So the search remains a problem of probability and optimization.
Yes, the too many unknowns problem. We don't know the location, the precise frequency, the polarization, or the modulation scheme of any potential signal. To address this, the search has shifted towards the development of highly sensitive multi-channel spectrum analyzers, or MKSAs, which can continuously monitor millions of frequency channels simultaneously, searching for that single elusive narrowband signal.
And if that signal ever arrives, that simple pulse sequence confirming intelligence, we then face the cruel reality of the cosmic speed limit, the inevitable delay.
The time lag.
If that definitive signal originated from a star 50 light-years away, establishing a two-way radio conversation means we send our reply, and then we must wait 100 years for their response.
A full century.
And if the source is 500 light-years distant, the conversation becomes an exchange spanning a millennium.
It demands a commitment that really transcends human lifespans. However, the sources remind us that the exceptional importance and value of such a conversation, the transfer of knowledge potentially accumulated over millions of years, would undoubtedly justify the delay.
It would be a slow dialogue.
Spanning dozens of human generations, but the reward would fundamentally reshape human civilization.
This inherent delay forces us to move beyond the immediate scientific challenge and consider the generational impact, knowing that any reply we send will take centuries to return, and that the person who reads the answer will be born long after we are gone. It elevates the exchange to a monumental act of trust and intellectual legacy. So here's the final provocative thought we leave you with. If humanity were to receive a definitive artificial signal today, and we knew the next reply would take hundreds of years to return, what single, most valuable question, encompassing all the knowledge, struggle, and curiosity of our civilization, would we choose to send to that advanced extraterrestrial civilization? Think about the weight of that question as we wrap up this deep dive.